All right, well, let's go ahead and get started, and I'm sure people may continue to filter in, but I think we have the little chime turned off, so hopefully it's not disruptive. So ResFrac in brief, our objective is to maximize economic returns. We do so by simulating the entire life cycle of a hydraulically fractured well in a single model. So that means fracturing, leak-off, closure, production, child wells, EOR, refracking, etc., and preserve the realism and fidelity of that solution in a single model. The simulator is coded to be very broad in applicability, so it is equally applicable to conventional or geothermal operations, although the bulk of what our users use it for is on the unconventional side. So to simulate the entire life cycle of a well, you need to be able to simulate fracture propagation and proppant transport, the multi-phase production that comes out of wells, as well as any of the geomechanics that evolve throughout the life of a well. And ResFrac is doing so in a single coupled simulation. So this is an example of a parent-child setup. The well on the left is my parent well. I'm fracking that well right now. I'm going to frack a second stage, then I'll produce. I'm showing pressure in the bottom right. So we'll see pressure deplete in the fractures as well as the matrix. After 3 years, I then come and I frack my child well. You'll see that those fractures preferentially grow into and intersect my parent well, which is a direct consequence of that depletion and the geomechanics that has changed. So the experience we'll draw upon today comes from both licensing our software as well as providing services to our clients. Those clients span all of the Americas, from Montney in Alberta down to Vaca Muerta in Argentina. And that is the 90-second overview. Please limit questions today to the technical nature. If you'd like to talk about commerciality of ResFrac, feel free to reach out to me afterwards, and I'm more than happy to have that conversation with you, but want to make sure that conversation today remains technical. So with that, I'm going to turn it over to Mark for a pretty exciting session that we have for him to kick off, which is that we are pushing a major UI update this week, which includes several new features, which Mark is going to go ahead and preview for us to show what he's been working on.
The update this week has a lot of things. I'm going to demo these, but just really quickly, you can now make plots in the builder of, like, for example, the inputs that you put into the table, so you can preview your inputs. You can make 3D plots to preview the well setup, the locations of the matrix mesh and the formation tops and so on. Another really big one is that the simulation mesh can now rotate directions. So traditionally, we've asked that the user try to align the simulation mesh direction with the direction of fracture propagation. That may not be north-south, and that's been confusing for people because that meant that the coordinate system was not north, south, east, west. So now the mesh can rotate, which allows you to use a true north coordinate system. So I'll talk through that. Several things to support that change. So in the 3D visualizations, you can now stretch the visualization in the direction perpendicular to the fracture propagation direction, and that's rotated, so it doesn't have to just be an X or Y direction stretch. I've put in some new wizards to help with the well importing and setting up. So we just gave it to someone the other day as a test, and he said in 10 minutes he'd imported 5 wells and completely set everything up. So that, I think, should make a lot of people happy. I think that's been one of probably our top pain point for users, has been importing wells and getting them set up. We have a wizard now that will set up properties versus depth, like from example from a well log, wizard for setting up production sequences, and also a correlation for having multiple fracture strands. So we'll try to rip through that today. Also just want to talk about what we have coming down the pike next month and the next year. The most immediate thing is, first off, we have a new developer in the company, Chris Hewson. He's based up in Calgary, and I've had him working exclusively on speeding up the simulator. So he's done some great work on improving the solver performance, and has a version of the code that's not yet released that's running simulations 2 to 3 times faster. The more speed up, the bigger the problem is. So the slower the simulation, the more it's going to speed up with that update. So that is undergoing testing and polishing, and is going to be released at some point this month. So I think that'll be a very popular update. And really, there's a lot of additional room for him to run. So he's going to be working on that throughout the year. And there's a lot of things I think we can do to speed up the code a lot. So you're seeing a 3x speed up this month. There's going to be a lot more speed up happening this year, thanks to Chris, who's delegated to that work on that full time. Another request we've had a lot recently has been, can we write a computer program that will submit simulations? I'm going to submit simulations not through the user interface. That might be, for example, if you have your own history, let's say history matching algorithm or your own scripts to run sensitivity analysis simulations, and you want to code that all up yourself. You're kind of a power user. And so that command line interface submission is something that Soma Metam has been working on for the past month, and that's also going to come out in the coming weeks. So those are very, very close updates. Next thing, like for me personally, the next big thing on my to-do list is finally to put in support for importing corner point grids. So getting this big update out this week is going to help clear off my to-do list to get to the corner point gridding. As I said, there's going to be a lot more simulator speed-ups occurring as Chris has more time to work on it. And then looking a little further out, approximately the fall, we'll be coming out with automated sensitivity analysis, history matching, and optimization. So we've got Charles, Kang, and Soma working on all of the cloud backend and the algorithm side of that, as well as several really good user interface people who are building the user interface integration. So we're trying to make it really easy to set up, for example, a history matching algorithm inside of our user interface. And then probably the next thing out, so this hasn't started work yet, like the rest of the things on this list, but I want to put in a fast-running approximate frac simulation model. So, rather than doing a detailed mesh of every fracture, can we use something a little more approximate, and that would allow you to run, full wells, full pad type simulations. And so that's something that we have on the development pipeline as well. That would be an option. So basically you'd have an either or. You could either do a more detailed, fully 3D discretization of the fractures or the fast running approximate. So just wanted to give that, you guys don't see that, but that's a huge part of my job and a huge part of my day-to-day is pushing all these improvements out all the time. And really appreciate all the feedback we get from you guys. That really helps with that. All right, so to go into the user interface, so this is the not yet released version of the user interface. And I've just opened up the default simulation that ResFrac gives you. First, you can see this button up here. This is pulling up a 3D preview of the simulation. So this is actually the well and the matrix region. You can see that this is a slightly stripped down version of the 3D visualization tool. It doesn't have everything because you don't need everything. But this, of course, allows you to really quickly iterate and make sure that the simulation you're setting up is what you expect. So the next thing I want to talk about is this problem of needing to rotate the mesh, which you no longer need to do. So you might recognize this figure. This is talking about how in the past we always tried to align the fractures with the y-axis, and that meant that the y-axis was not north-south. So we are not going to do this anymore. That's turned out to be really confusing to people. So there's a new button here called Rotate Simulation Mesh to Align with Stresses. I'm going to check that. And then I'm going to go to the Static Model and Initial Conditions panel, and I'm going to say, okay, the direction of SH max is, let's say, 110. So now the y-axis is actually north-south, and so the direction of SH max is actually 110 degrees east of north. So if I click here on the preview, I'm going to click refresh. It's going to reload, and now we can see what's changed. If I turn on the ruler grid for the matrix, I'm going to click that, show the axes. You can see here now the simulation mesh is aligned with the direction the fractures are going to propagate, and that is no longer aligned with the X or Y axes. So that's really handy. As you know, we like to stretch out the the visualization in the direction that's perpendicular to the fracture propagation direction. So I can click here. Now it has a stretch direction, which is defaulting to be the correct direction. So I'm going to do a horizontal stretch of 10, and here we can see it's now stretching out that region. So you've got a rotated stretch. All right. So how does that play into something like a, let's say, importing wells? So I'm going to go ahead and go here to the Wellbore Survey Import Wizard. You may recognize this. Oh, actually, first I'm going to delete the well that was in there. So I'm going to get rid of that. Go Well Survey Import Wizard. I'm going to go to Well Demo. And so now we're going to put in the actual XY position of the well. So the Y-axis will mean north-south. The X-axis will mean east-west. And so you could use, actual, northern easting coordinates for the wellhead position. Here, I'm just going to put it at 0, 0. Wellbore inner diameter. And this is a new parameter, the optional recentering measured depth. I'm going to have it automatically recenter the matrix region at 11,000 feet of measured depth along the wellbore. And so here I have an example wellbore survey here, measured depth, inclination, and azimuth. I'm going to copy and paste that in here, and I will click apply. Okay, so I can go up here and see what that looks like. I've got to click refresh. All right, so there's my new imported well. You can see there, it's a little more realistic looking than the kind of L-shaped well I had before, and this matrix region has been centered at 11,000 feet of measured depth. And again, you can see that if I put on the ruler grid, the matrix region is not aligned with one of the axes. Let's go ahead and import a second well. So I'm just going to call it Well Demo 2. And I'm going to move the wellhead position a little bit. So I want the wells on top of each other. Otherwise, I'll leave everything the same. I'll click apply. Go up to the visualization and click refresh. Cool. So now I've got 2 wells, and they're offset by that amount. And there we go. So we're making some good progress. Now, the next thing I might want to think about is I want to make sure these wells are landed in the correct zone. So keep in mind that, in reality, formations are dipping. And so in ResFrac, we're putting in formation properties versus depth. Soon we'll have a corner point grid import capability, but here you can see you've got properties versus depth. Of course, this properties versus depth is only valid at a particular location since the formations dip. So you might import your wells and then find that the wells are not landed directly in the right zone. So for example, I've turned on facies here, and you can see that the facies I already had loaded into the simulation are at a completely different depth than these wells. So we have a wizard that will simply adjust to those well depths to make sure that the well is landed in exactly the right place. Because it's not really important to match depth so much as put the well in the right zone. If it's a middle Bakken well, it needs to land in the middle Bakken. So going back to wells and perforations, I'm going to adjust well landing depth wizard. I say, please apply this to all the wells. I want you to land in the pay zone. If I want to adjust the matrix region depth, I'd say yes. So in other words, here the matrix region is this blue cube. That's where the stimulation is occurring. If I deepen the well, I don't want to leave the cube up there, so I want to deepen the cube as well. So I'm going to adjust the matrix region depth, and I want to put it halfway right in the middle of the pay zone. So I'll click apply. And what it's doing is it's actually changed these wellbore vertices here in order to land the well in the correct place. So I can click refresh. And now here we have it. If I turn on the facies, you can see there it is. Now the wells, they've been deepened, and they're landed smack in the middle of the pay zone. So making some good progress here. There's one more thing I want to do, which is I want to set up the stages, and I want to set up the perforations. So I will go to the well stages setup wizard. You can see here I have a lot of description of this wizard. It's kind of a complicated wizard. So what I put in is, keep in mind that we're only modeling a section of the well. So it's how wide is this matrix region that I'm going to kind of mesh. And so I'm going to say this in measured depth along the wells. So let's say I want to model 500 feet of measured depth along the wells. Let's make it 400 feet. What's the stage length per well? I'll say 200. So it's going to put 2 stages into each well. I will click. Let's see if I have anything else. I could recenter the matrix region right now, but I don't want to do that. I'm going to leave it where it is. So I'll just click apply. And so now what it's done is it's actually set up stages. So let me scroll. I have a really small monitor at high resolution, so it's hard to fit everything on the screen. You can see here stage number. If I scroll down to the bottom, oops, oh, I'm missing a scroll bar. This is the wrong version. All right, so if I scroll down to the bottom, sorry, stage 0 here, that's at the toe of the well. That's the part of the well that we're not including in the model. So like out here, that's of course in reality it's there, but as far as the model is concerned, we're not going to frack in that part of the well. Then these vertices represent the first stage. These vertices represent the second stage. And then stage 3, this is the entire rest of the well, but all the way up to the top, to the surface. That's the part that's not part of the model either. So I've set up 2 stages. Note that it had to probably insert some wellbore vertices to make sure the stage edges were in just the right place. So if I click refresh, now I can turn on the perforations, turn off the matrix, and what we see here is it's placed, it has placed perforations right smack in the middle of those 2 stages. So by default, it's using the inline treatment. So here I'm saying how many clusters I have per stage. So for example, I can make that 1. And then if I go back up here and click refresh, turn on the perforations, we'll see that that stage now just has 1 perf. So, I mean, just so you can see in a pretty short period of time, I just imported my wells and set that up. So that's a huge improvement over what we had before. I think that'll be quite popular. Other cool things, so note that now we've got this line plotting that we can make. So here's, for example, my black well table. I can click this button right here.
Mark, if I can pause you for 1 second.
Yep.
To see if there's questions on that import process.
Okay, sounds good.
You had sent an email previously. This should fix the error or confusion that we were trying to resolve previously with that example that you had sent.
Yeah, that does help for sure. Yeah, I mean, it pretty much solves about everything that I was dealing with. The only thing I was also looking at offsetting perfs, which, I still can't do with the inline method because the inline method by default lines everything up for the most part. I mean, I could offset the wellhead location to do that. It's not a big deal. Yeah, I think that's a great step forward, especially visualizing it. So
Hey, Mark, I had a quick question about, by the way, this is really amazing. This will make life a lot easier.
Yeah.
The perforation, if I'm entering the perforation in an actual wellbore, or the clusters in an actual wellbore, and I'm not using the stage setup wizard, is it possible to do that by just using the measured depth of the perforation cluster in this version, or is that not possible?
Well, the perf import methods are the same, so you can change everything I just did. So it's defaulting to do this, inline method, but I could just turn that off here, and then I can just specify the explicit locations of the perfs as usual.
Yeah. Got it. Thanks.
Okay. All right. Thanks, guys. So some other stuff to show off. So for example, here's my fluid panel. I click this 3-bar icon. It's going to pull up a line plot of different things. So here, this is RS, BO, and BG versus pressure. And if you click the gear icon, you might actually find that there's additional things that you might be able to visualize. So for example, I could also be visualizing oil viscosity, for example. So this is the same visualization tool that we have in the visualization tool. And this is useful. Note that it's not just plotting the numbers in the table. So for example, this is the bubble point pressure that's been inputted. And so rather than showing the saturated BO from the table, it's finding, hey, we're at that saturation point, and then this is the behavior of BO as pressure goes up beyond that. And that can allow you to do things like, hey, if I want to maybe go from basic option and turn on correlations, then you could You can refresh, and then you can see how the correlations slightly tweaked the behavior of the viscosity and the BO a little bit. So that's pretty cool. I want to show a particularly complicated one that I had to implement, which is for the compositional model. So if I go to compositional, go to fluid model options. So I'll use the wizard to set up a quick compositional fluid model. Now I can click the bar icon. It's actually done an entire constant composition expansion. So it actually used the Flash calculation engine to calculate, for example, the saturation pressure, the change in relative volume. You can even plot up, for example, the the viscosities. So you can see the viscosities that come out of the LBC model. So here we've got, this is oil viscosity. So this is not merely a regurgitation of the numbers you put in the table, but it's actually doing a lot of calculations. It's actually sharing. We've pulled in some of the code from the simulator, and it's directly using the same code or very similar code. So that also should be a lot of help. Another cool one that I want to show here is this properties versus depth wizard. So here what I'm going to do is I have a table that this is permeability, porosity, Poisson's ratio, water saturation, Young's modulus, pore pressure, BO coefficient, and stress. All of those defined every 6 inches along about a 600-foot interval. So I don't want to have 1,200 layers in ResFrac. I'd like to upscale this into a smaller number of layers while still honoring these properties. So I can do that. So I guess I'm going to import 8 properties. I want this target layer thickness to be 50. It might be less, it might be more. If I want to, I can manually say, hey, I want to make sure you put a layer boundary at a certain depth or multiple depths. I will skip that for now. All right, so I'm going to select which properties I'm importing. Let's see, so I've got permeability, porosity, Poisson's ratio, saturation, Young's modulus. All right, Poisson's ratio, saturation, Young's modulus, and pore pressure, BO, and SH min. Okay. All right, so those are the 8 parameters I'm importing. I click next, and here is a table asking for those properties. And so I'm going to come in here to this table. I will select all, paste it in. Okay, we'll click apply. And the algorithm is actually going to go through this table and automatically pick where to put the layers. So we can see here that it's upscaled that 600 feet into 40 layers. And neato, I can click on this 3-bar tool here. And here's actually a plot. Note that depth is on the x-axis. I know it would be nice if it's on the y-axis, but that turns out to be complicated, so we didn't do that. But here I actually have water saturation versus depth upscaled from that, every 6 inches data into something that's more tractable. So here, all of those properties are available here. So I could go to porosity or whatever, and we can see how those things are changing. So this also should be a lot of help in setting up simulations because it's a pretty common situation to have a well log. Now this does not currently directly import from an LAS file. I've written that code, but I'm not finished debugging it and testing it. So it's not in this release, but later this month an update will include the ability to directly pull this data from an LAS file. In the next couple of weeks, you'll just have to take it from the LAS file, put it in a spreadsheet, and then copy and paste it over. So again, hope that's useful. Let's see what else. Another wizard is here in well controls. We really do not recommend that you change production rate or pressure daily. Every time you change a wellbore boundary condition, it creates a little mini pressure transient in the simulator, and it has to take a bunch of time steps, and that slows it down. So this production sequence wizard, which I won't demo right now, it's got quite a bit of options here, but effectively what you're going to do is you could put in, for example, daily production rate, and then it would automatically average that into like a monthly or bi-weekly production rate. It would not only automatically make the average, but then it would create a production sequence down here in the controls. So let's see what I've not covered yet. Yep, I've pretty much covered everything. The one thing I'll also mention, seen this Lawrence Livermore paper on, let's see here. It was at Hydraulic Fracture Technology Conference, really nice paper, where they looked at how if fractures are actually fracture strands, how does that affect the toughness and the viscous pressure drop? And we've actually implemented a very similar correlation into ResFrac. So I won't cover that today, but I have a blog post that I'll probably put out this next couple of weeks where I summarize that. So effectively, there's three things. Number one, well, actually, let me see. You know what? I think I have some pictures handy. Let me see here. I do. Okay. So this is from the release notes that we're going to put out. So the three things. Number one is they find that toughness should scale with the square root of the number of strands. So if I have like 9 strands, then toughness would be 3 times higher. So that's fine. Although you might note that we already have the ability to increase toughness from within ResFrac, right? We already have this relative fracture toughness scaling parameter. So, you know, this correlation can be used to increase toughness, but that's not like kind of a qualitative change because we already did that. The second thing, they don't talk about this, but if you have multiple fracture strands, it should increase leak off. So that's not in the food paper, but clearly I think something really important. So we've put in that the leak off scales with the number of strands, and actually because leak off scales with area times the square root of permeability, if you have 9 strands, that actually is effectively like making the leak off permeability 81 times higher. And so we mimic that as a pressure dependent permeability. Again, note that we already do that. So we already have tables of pressure dependent permeability during fracturing to account for accelerated leak off. When those fractures close up, the unpropped fractures close, we assume they don't contribute to production, but we think they're important for leak off. So that's also something the correlation has implemented inside of it, but again, that's not a new thing. But there is kind of one qualitatively new thing, which is also the effective viscosity will scale with the square of the number of strands. So if you have 9 strands per quote fracture, that would make the effective viscosity 81 times higher. That has a material impact on the simulation results, and is not something that we actually did have the ability to do that previously, because you could set a so-called maximum fracture conductivity, but it wasn't something we did very often. But it really impacts symmetry of the fractures. So this is like an initial base case. You can see how asymmetrical the fractures are. And this is a simulation where I have 10 strands. So 10 strands is a lot. What we're saying is every single one of these individual cracks is actually a strand of 10. 100x more viscous pressure drop. And when you have more viscous pressure drop, it promotes symmetry. It promotes symmetry because if the crack tips are different distances from the well, then a crack tip that's closer to the well will feel greater pressure and then be more likely to propagate, and this way they equilibrate. So this is an interesting thing. Basically, I think what we're going to do within ResFrac is over the coming months do some of our own work to test out different numbers for this strands, you know, how many strands are in each fracture. And I think we're going to do a little bit of testing. But sometimes, you know, I actually think that fractures are often very asymmetrical. So I'm very comfortable with the asymmetrical fractures we show now. And I think it is a mistake to try to make them all look perfectly symmetrical and the same. And we have field data to suggest they're very often asymmetrical. But on the other hand, sometimes, you know, we get pushed back. And so I think that we may do this to some extent. I don't know that I think fractures are all exactly this symmetrical, but, you know, maybe we're going to start using a fracture strand parameter of 4 or 2, and then maybe not 10. But that's something we're going to look at in the future. So that's, I think, probably the most material in terms of the simulator new change in this update. I think it's something that's interesting to experiment with, but is still a little bit on the research side until we've had a chance to kind of test it out more and decide how much we really think this is the right way to go. All right, so I believe I have covered my content.
Coming back to multiple fracture bands, there was
okay. Well, anyway, here. So I don't see the questions, but let me just say I am done. So I would be happy to take questions.
Oh, okay. Yeah, so I think there's two kind of segments that we covered, and I neglected to pause you in between, so I apologize. There's kind of the new upscaling wizards that were separate from the Wellbore wizards, and then there's this multi-strand fracturing theory. However, there's one question right now in the chat on the multi-strand nature, which is Mark saying that leak off is proportional to A times square root of K?
Yeah. Absolutely. It is.
And so that's where previously we had a PDP table, right? Where in the ResFrac software, the thought was we're using a planar fracture to actually represent multiple fractures. And so because there's that non-uniqueness between fracture area and permeability, to mimic the additional area from multiple fracture bands, we could input a PDP table where permeability was increased during injection and then reverted back to original during production. But with the most recent code update, you can actually just use multiple fracture bands to simulate.
And under the hood, it's actually creating a pressure-dependent permeability table. So it's doing the same thing. That's what we've always said. So I'm trying to find the insert equation here, but I don't know where it is in PowerPoint. But the cumulative volume of fluid that's leaked off, if you assume Carter leak off, which of course, leak off is not always Carter leak off, but it's a good kind of first starting point. The volume of fluid leaked off is 4 times A times the leak off coefficient times the square root of time. And the leak off coefficient is proportional to the square root of permeability. So we can see that there is an A square root K. That A square root K, this equation, by the way, if you just reverse the sign, is the same as the RTA one-dimensional production. So the RTA equation for 1D production is identical to the Carter leak-off solution. Just flip the sign. And of course, the fluid pressure. Oh, and you flip the sign because the fluid pressure in the fracture is different. So yeah, effectively what we do is if we think that there's 5 strands, then area is 5 times greater. That means that that's equivalent to making the permeability 25 times greater. And it will result in the same amount of leak off.
Okay. So then a question which you touched on, but we can return to, which is how is the multi-stranded fracture behavior incorporated into the simulator?
So I think I answered that question, right? So there's 3 things. It's the viscosity is higher. And actually it's a little more complicated than that because we have non-Newtonian fluid. So what you really do is you make the conductivity lower. And then in addition, the effective aperture that you use to calculate the shear rate in the power law fluid model is changed as well. So it's a little more complicated than that, but effectively there is more viscous pressure drop, number 1. Number 2, it impacts toughness, and number 3, it impacts leak off. And that's how it's done.
More of an operational question is, how do you input that into the simulator? So do you specify a number of strands? Is that in advanced options? Sorry,
you specify a number.
There.
Yeah, you specify a number of strands. And it actually, I don't think it's in this version of the user interface, but it will be a number here that you can input.
Great. Then reverting back to the upscaling wizards, question was, which property is it based on? And I know it's multiple, so maybe explain a little bit on how the simulator is picking how to chunk the static model.
Yeah, so it's based on all of them. it looks at all of them, and based on the joint change of all of the parameters, it puts the chunks in. Suggestion I got from Dave this week was maybe I should allow the user to weight them. Like you could put in a number from 0 to 1 that's the weight factor assigned to each parameter. So like maybe you really don't want to use porosity when doing the chunking, let's say, but you want to include it in the import. So I think that's a good idea, and is probably like on version 2 of this that I'll probably do later in the month when we have kind of a second round of update. That would be a good idea. But at present, it weights all the properties similarly. And what I've done is I put in logic, like for example, 5% change in porosity is considered equivalent to a 25% change in water saturation, which is equivalent to a 200 PSI change in rock density and so on. So I've kind of put in like kind of scaling levels for each parameter. And then what the code does is it basically just, it uses a really, the way the algorithm works is it uses, it looks at the second derivative and the first derivative of the curves, and then basically ranks each point about how much things are changing. And then it basically uses a threshold that's quite conservative, so it creates like lots of layers, and then it's too many, and then it iterates until it's got about the right number of layers at once, which is usually going to spit back, or 50 to 100 layers, 40 to 100 layers, I guess. Another suggestion that Dave provided was maybe we should allow the user to plot the original well log as well, and that also is a good idea. I like that. We might put that in.
That was just written in the comments as a question.
Yeah, that'd be nice. But for now, you'll just have to go into Excel and make the plot. And if you look at our release notes, that's what I've done here. So here's an Excel plot of a kind of a generic neutron porosity log, kind of a generic example. And you can see how all the features in this neutron porosity log are captured here in the upscaling. Right, so you can see there's 2 peaks there, there's 2 peaks, there's the peak, there's the peak, there's the peak, there's a peak, etc.
Yeah, I might expand on that as well, in that you can, as a workaround as well, you could go from the table in the UI and copy those into that same Excel that you started with. So in Excel, you could plot those properties on top of each other.
Yep. Anybody else have any other questions or comments? I'll make a comment that I noticed today or yesterday. Again, I'll reiterate the point that if you change the boundary conditions all the time, then it way slows down the simulation. So I like to, personally, when I'm doing this, I'll change it maybe once a month. Like if I eyeball that bottom hole pressure first time and it looks like the bottom hole pressure was about constant for 3 years, I'll just use one bottom hole pressure for 3 years. Don't feel like you need to change things every day or every week. You're just putting in a lot of detail that's not really going to have a big impact. So I'll make a point, which is that if you have a lot of wells, you might want to synchronize when they change. So this is something I just noticed, and I'm probably going to put in a warning or adjust the wizard or something to help people with this. But somebody sent me a simulation with 7 wells, and the wells were changing once a week, but they were all out of sync. So in practice, a boundary condition changed about every single day. And again, every time you change a boundary condition, it's going to slow down the simulator. It's going to take a bunch of time steps to capture that. So, changing a boundary condition every single day for 10 years, that's just going to force the simulator to take tons of time steps. So be aware of that, and maybe try to, if you have a lot of wells that you're putting on production sequences, number 1, just feel very free to not change the boundary conditions very often. But number 2, you might consider making sure that they're synchronized. So if you're going to change once a month or once a week, at least make sure that they're all changing at the same time. So that's a good pointer, something that just kind of occurred to me this week that could be useful to some folks. All right, well, if that's it, I have no problem finishing a call early. Anything else, Garrett?
That's all I have. I'll have to dig up some more material for my Tuesday tidbit for next week. But
sounds good.
look forward to everyone joining us again next week. And don't know the topic yet, but I will be brainstorming and solicit suggestions as well.
Thanks everybody for joining, and yeah, I hope you enjoy all that new stuff. It's been a lot of work under the hood to make all that happen. So thanks to the whole team for that.